Hey everyone. Welcome back. To start today's masterclass, we need to clear up a big myth in the database world. A lot of older engineers look at modern graph databases and say, wait, didn't we already try this back in the 1970s with the codacil network model? The answer is no. Let me explain why. In the 1970s, the network model forced developers into a nightmare. You had to define incredibly strict rules about exactly which records were allowed to connect. And worse, to read your data, you had to manually write computer code that followed pointers step by step through the hard drive. Like navigating a dark maze. Modern graph databases threw all of that away. In a modern graph, any node can connect to literally anything. You don't have to walk the maze, you can teleport directly to any data point using its ID. And best of all, you use declarative query languages. You just tell the computer what you want, and the query optimizer acts like a smart GPS, finding the fastest path for you automatically. Now, speaking of query languages, let's look at one of the oldest and coolest ones, Datalog. Datalog was built by academics in the 1980s. It is much older than modern languages like Cypher or Sparkle. While most software engineers have never heard of it, it is incredibly important because it provides the foundation for how we think about logic. In fact, because modern computer CPUs keep getting more and more cores, many scientists believe that logic-based declarative languages like Datalog are the future of parallel programming. Today, you can actually see it being used in powerful systems like Datalog, and in Hadoop datasets via Cascalog. But Datalog looks a bit different. It is based on a language called Prolog. If you remember triple stores from our last video, we wrote sentences like, subject, predicate, object. For example, Lucy, born in Idaho. Datalog flips this around to look more like a standard programming function. You write the predicate verb on the outside, and pass the subject and object inside the brackets. Look at the code on screen. We write, name, parenthesis, Idaho, comma, quote Idaho unquote. Then we write, born in, parenthesis, Lucy, comma, Idaho. These are not queries. These are called facts. We are simply giving the database a list of absolute truths. So, if there are no select statements, how do we actually search the data? We teach the database how to think like a detective. We do this by giving it rules. A rule takes small facts and combines them to derive new facts. Look at the code box. Step 1, we tell the database a fact, Idaho is within the USA. Step 2, we give it another fact, the USA is within North America. Now, we write a Datalog rule that says, if location A is inside location B, and location B is inside location C, then A must be inside C. Using that rule, the database automatically deduces a brand new fact, Idaho is within North America. The database applies these rules recursively, over and over, piecing clues together until it answers your final question. It takes a different mindset to write but it is incredibly powerful for massive, complex data sets. Alright. That brings us to the end of our journey through data models. Let us summarize the big three. First, we have document databases, like MongoDB. These are perfect when your data naturally comes in isolated, self-contained chunks, like a user profile or a blog post. They provide amazing read speed because of data locality. Second, we have traditional relational databases, using SQL. These are the gold standard for business processing. They shine when your data has many-to-one relationships, where things need to be normalized, cleanly separated into tables, and joined back together safely. Third, we have graph databases, like Neo4j. You use these when your data becomes a tangled web, where anything can potentially relate to everything else. They use brilliant query languages to navigate complex relationships effortlessly. Remember the rule of polyglot persistence: there is no one-size-fits-all database. Great engineers use all three models at the same time, choosing the absolute best tool for the specific job. Before we go, I want to remind you that the world of data is vast, and there are extreme edge cases that go far beyond the big three. For example, in biology, scientists use databases like GenBank to store DNA. They need to search incredibly long string molecules to find similar, but not perfectly identical, sequences. A standard SQL database completely fails at this task, requiring highly specialized biological software. And in physics, the Large Hadron Collider generates hundreds of petabytes of particle collision data. At that extreme scale, standard databases would cause hardware costs to spiral completely out of control. So they build entirely custom storage solutions. The world of software architecture is endless. Thank you for joining me in this chapter, and I will catch you in the next one.